All right, we are starting back with slide 35. I was finishing up explaining about milligrams per deciliter, and I was using the example of blood glucose levels. But this is slide 35, and I'll try my best to finish up the recordings of chapter 2A. During this recording, but I don't know, it may take another one. But I try to do at least for every set of slides. My goal is to cover it in 4 recordings, because that's a good amount. That's about an hour's worth of time, and it gives you time to kind of watch it at your pace and stop and pause and replay things that you need to, listen to again, that kind of thing. So anyway, I was telling you my daughter has type 1 diabetes, and I had to learn about blood glucose levels. And so when I check her sugar, it'll give me a number on the glucose meter. And if that number says 80, what that means is 80 milligrams of glucose per deciliter of her blood. So, and that's what those blood glucose readings mean, is milligrams per deciliter. So that's another way of representing concentration. We're mostly going to use percent, though. I mean, we really don't have any need for anything else in this class. Just use percent solutions. The slideshow talks about molarity and molecular weight and all of that stuff, and Avogadro's number. This is not chemistry class, so we're going to skip that. It is important in chemistry, not so much in what we're doing. So colloids. Colloids are also known as emulsions. They are heterogeneous mixtures. That means the particles are not evenly distributed throughout the mixture. You can actually see large solute particles in solution, but they don't settle out. So this gives the solution a cloudy or a milky look. So their examples would be Jell-O, but we don't really deal with Jell-O in this class, but sometimes in lab we use a gel called agarose gel to grow bacteria on, and that would be a gelatin, and that would be a colloid. But in the cell, in all of the cells in our body, the semi-fluid solvent in there is called cytosol. It's found within the cytoplasm of our cells, and that is a colloid. And then we have suspensions, which are also heterogeneous mixtures, but the difference in a suspension and a colloid is that the solutes do settle out. Water and sand would be a suspension. Salad dressing, most salad dressings are a suspension. You can shake it up and it'll mix up, but then you sit the dressing bottle down, and everything settles out. All those solutes settle out. So blood is considered a suspension, because the blood cells will settle to the bottom if left sitting. We're going to skip on now to section 4, called chemical bonds. Chemical bonds are just strong attractions between atoms that form compounds and molecules. And the importance, subatomic particles that are most important in forming chemical bonds, that are essential in forming chemical bonds, are electrons. So we have to talk about electrons and their role in forming chemical bonds. Electrons can occupy areas around the nucleus called electron shells. And the ones that are most important in chemical bonding are the valence shell electrons. These are the electrons in the outermost shell, which is called the valence shell. The electrons in the valence shell have the most potential energy because they're farthest from the nucleus. These are electrons that are involved in chemical reactions. You do need to know the octet rule, or rule of eights. This is not going to be we're not going into as much detail with this topic as you would in chemistry, but you have to have a basic knowledge. And the octet rule says that atoms desire, and desire is a strong word for an atom. I don't know what atoms actually desire. Desire means like a conscious, wanting of something, but they are stable with 8 electrons in their valence shell. But most atoms don't have 8 electrons in their valence shell. So they'll either lose or gain electrons in order to have a complete outer shell of electrons, a complete valence shell of electrons. So some smaller atoms, though, like hydrogen and helium, they are exceptions to the octet rule because their valence electron shell is the first one, the first energy level, and it only requires 2 electrons in it. It doesn't need 8. It needs 2 to be stable or full. So after the first shell, all the other shells are full with 8 electrons in them. So the noble gases already have 8 valence electrons, or 2 for helium, so they're not chemically reactive. They're already stable, so they don't tend to combine with other atoms. They don't tend to lose, gain, or share electrons because they already have their stable octet of electrons in their valence shells. So most atoms do not have full valence shells. They will gain, lose, or share electrons, and when they do that, they end up forming chemical bonds with other atoms to achieve stability of 8 electrons in the valence shell. I don't know what's going on with my computer, but this sign keeps popping up, and I'm just going to click off of it every time it happens until I can deal with it. All right, so we have an example here of helium and then another one of neon. These are 2 inert gases or noble gases. Helium has only the first electron shell and it has 2 electrons in it, so it is already chemically stable. And neon has 2 in the first energy level and 8 in the second. So its outer energy level is full with 8 electrons. It's already chemically stable. But then you have these examples, hydrogen, carbon, oxygen, and sodium, whose valence shell is not filled. Hydrogen needs 1 more electron to fill its valence shell, which is just the first energy level, right? So carbon needs 4 more. It's got 4 already in its valence shell, but it needs 4 more to have 8. Oxygen needs 2 more. It has 6 right now, but it needs 2 more to have 8. And sodium's a little different because sodium has 1. So yes, if it got 7 more, if it gains 7 in this third energy level, in its outer energy level or valence shell, that 7 would give it the 8 that it needs. But it would be a lot easier if it just lost this 1, because if it lost this 1, then it no longer has a third energy level, and the second energy level is already filled. So sometimes an atom is going to lose electrons because that's easier than gaining. Losing a few is easier than gaining a lot. So sodium, to be stable, would lose this 1 electron. And you don't have to look at diagrams of atoms and figure out what happens to them. I just want you to listen to me and try to understand what I'm saying. You really just need to understand what an ionic bond is and how it forms, what a covalent bond is and how it forms, what hydrogen bonds are, how they form, and then what that means for us in this class. So you're never going to have to look at pictures of atoms and analyze. It's not going to be like that, okay? So there are 3 major types of chemical bonds: ionic, covalent, and hydrogen. Ionic bonds form from ions that have opposite charges because opposites attract. So ions are atoms that have gained or lost electrons, and when they do that, they take on a charge. So if an atom gains electrons, it's going to take on a negative charge. If it loses electrons, it's going to take on a positive charge because it will have more positive protons than it does negative electrons. So gaining electrons will make a negative ion, and losing electrons will result in a positively charged ion. And another thing is that in ions, the number of protons does not equal the electrons. Kind of goes without saying. So ionic bonds involve the transfer of electrons from one atom to another. If an atom loses an electron, it transfers it to another one that gains an electron. So the one that gains becomes an anion, or a negative ion, and the one that loses an electron becomes a cation, or a positive ion. And because they are oppositely charged, the two ions are attracted, and that's the ionic bond. The most common example that is given in science classes for ionic compounds is sodium chloride or table salt. So if you start out with the sodium atom, it's got that extra electron that it needs to lose in its third energy level. And the chlorine atom has 7 valence electrons. So the sodium can transfer that electron to the chlorine atom, and then you will get sodium with a positive charge because it lost 1 electron, and you'll get chloride, the chloride ion, with a negative charge because it gained an electron. And because the sodium is positive and the chloride is negative, they're attracted to each other because opposites attract, opposite charges attract, and that attraction forms the compound sodium chloride. That is an ionic bond. Most ionic compounds, not just sodium chloride, but you can also have like potassium chloride, sodium bromide, there are different ones. Anytime you have a cation chemically bonded to an anion, they're almost always called salts. And when they're dry, salts form crystals. An example is sodium chloride or table salt. And here is a picture of table salt in nature, crystals of sodium chloride. And then here is an illustration of how the sodium and chloride atoms are arranged to form a crystal. Now we're going to move on to covalent bonding. Covalent bonds are formed by the sharing of valence shell electrons. So you can have polar and nonpolar covalent bonds, and we'll talk about the difference. But here's an example where, I'm just going to do a different example. All right, so let's look at the example of oxygen gas. Okay, I guess I'll use the examples they have. All right, so we have 4 hydrogen atoms, we have 1 carbon atom, and when they combine by covalent bonding, they become methane, or CH4. Each hydrogen needs 1 more electron to be stable. Each carbon, or the 1 carbon that we have, needs 4. So if the carbon shares an electron, one of these 4 electrons with each hydrogen atom, then you've got hydrogen satisfied with 2 valence electrons. Look at every hydrogen. 2 valence electrons, 2 valence electrons, 2 valence electrons, 2 valence electrons. So all the hydrogen atoms are satisfied. They're stable because their first energy level is filled with 2. And then for carbon, you have 2 plus 2 plus 2 plus 2 is 8. So the carbon has 8 electrons in its valence shell by sharing 1 with each hydrogen atom. So it forms what we call 4 single covalent bonds, because a single bond is when only 1 pair of electrons is shared. And this is how you would write the structural formula for methane. The chemical formula is CH4. That's what we call the molecular formula or chemical formula. And the structural formula is where you draw the bonds out, like you see here. So that's an example of single covalent bond. Oxygen gas is 2 atoms of oxygen. So if you look at oxygen, if they share 2 pairs of electrons with each other, the oxygen on the left started out with 6 valence electrons, but when it shares 2 with the oxygen on the right, it now has 8. 1, 2, 3, 4, 5, 6, 7, 8. Go with this oxygen on the left. And it would be the same for the oxygen on the right. Now, by sharing 2 electrons with the oxygen on the left, it now has 8 valence electrons. So both oxygen atoms have 8 valence electrons in their outer shell. And since they're sharing 2 pairs of electrons, that is a double covalent bond. And nitrogen shares 3 pairs of electrons. So look at the nitrogen on the left. It now has 1, 2, 3, 4, 5, 6, 7, 8. And the one on the right is the same way. So nitrogen gas, N2, forms a triple covalent bond because it shares 3 pairs of electrons. We're going to go in the next recording, we're going to go into nonpolar covalent bonds where there's equal sharing of electrons, and polar covalent bonds where the electrons are not shared equally between the atoms.